Well, if you watched my last video on nonlinear geometry, you know that it has a major effect on special relativity, Einstein's first major theory. And it was all about light. So today I'm going to talk about light. Now, Einstein's special relativity and its previous photoelectric effect actually came from someone else. Its basis was on Max Planck, an astrophysicist and a quantum physicist, the first quantum physicist in fact. He invented quantum physics itself and was a major influence on special relativity and the photoelectric effect. I'm also going to talk about that. Basically, he was challenged by Germany to figure out the most efficient way to light a bulb to emanate the most amount of light and the least amount of heat. What he figured out is that basically the wave interpretation of light that you've all learned at school is completely useless for doing this. Instead, in what he called a fit of desperation, and basically he was pretty much completely upset by it, he thought of light instead of a continuous wave, as you can see here, but more like a particle or a photon. At the time he called it a quanta. It was based off of Newton's idea that light was a particle called a corpuscle. Basically, he found out that the ether, which is basically this thing that surrounds the entire Earth and the entire universe, which light travels through, doesn't exist. Scientists didn't believe him anyways. And basically, it was figured out that light travels through nothing. That means that light had to be a particle. Then later on, Thomas Young, a physicist, managed to make an experiment called the double slit experiment. He found out that light was actually a wave and not a particle. So that definition stuck around. I'll talk about the double slit experiment in a later video on the photoelectric effect, but for now we'll stick to special relativity. So basically, Planck found out that quanta could be equally useful for mapping out what light exactly was. And yes, he actually won the bet and found the most efficient way to light a bulb, heating it to a certain temperature so that the quanta, or what he called packets of energy, carried more energy out for a lower amount of heat. Brilliant, done. But Albert Einstein, the guy I'm going to talk about, actually made this into a much greater phenomenon. He called the quanta in his photoelectric effect an essential part of understanding the universe. And later in special relativity, he made several laws about them. For one, he figured out that the ether didn't exist. He did away with it completely. In fact, there was several experiments that were mapping out how to find out the speed of the Earth through this ether. They thought it was a light gas that permeated everything. And, well, they all failed. Einstein figured out that these experiments could all be explained if the ether didn't exist, and if light was a particle. Not exactly, though. He figured out that light was both a particle and a wave at the same time, based off a physicist named Louis de Broglie, a French physicist who actually figured out the same thing, and Einstein basically nicked it. So, as you can see here, this is one of the main laws that he figured out for photons. That, for photons, time doesn't pass. Now, as you know, photons in light travel at 300,000 kilometers every second. Photons, however, don't know this speed. They don't know this time. For them, time isn't even relative, it isn't even absolute, it is non-existent. Simply because they're traveling so enormously fast, it just doesn't work for them. And he figured out several thought experiments of how to explain this. One of them was the major thing known as time dilation. It's more in general relativity, actually, but basically he figured out when an object moves at a sizable fraction of the speed of light, let's say that this object, this hypothetical rocket ship, so be it, moves at half the speed of light. He figured out that if a clock were to be placed on this rocket ship, it would actually run much slower than a clock placed on Earth, which we'll just say for now is moving at 0% the speed of light. And therefore he figured out that time slows down the closer and closer you get to the speed of light. And so a photon who moves at the speed of light would move at such a fast speed that it doesn't experience time. photons emanated from the Big Bang would not know that 13.8 billion years has passed. They would just pass through it in a second. The next thing that special relativity states is from my previous lecture on Riemann or nonlinear geometry for using a three-dimensional axis to map out a two-dimensional phenomenon. In this case, Einstein used the Earth-Moon position system, with the Moon orbiting around the Earth and the Earth stationary relative to the Moon. As you can see, it makes the spiral pattern. He used this to calculate several factors of light coming from the Moon to the Earth. So, he also devised several thought experiments about light itself. Okay, I want you to imagine something. Imagine that you're a train. Not exactly a train, you're a person inside the train, sorry. And at the center of this hypothetical train, which by the way is again moving at a sizable fraction of the speed of light, you don't notice it though. At the center of the train, there's a light bulb. And when the light turns on, light will travel from one end of the train to the other, and it will travel from both ends of the train all at the same time. So I want you to tell me something. Which end of the train will the light reach first? And I'm going to give you a second to think about that. Okay, I'll tell you the answer. It will reach both ends of the train at the same time, as long as you are viewing it from inside of the train. Because to you, the entire train is stationary, even though it's moving. This train is stationary to you, and thus thus you are stationary compared to the light, and thus you see it moving in the ordinary way. However, I want you to now imagine that you're outside this train, which is also transparent, by the way, so you can see the light bulb. Now, I want you to, again, think which side will the light reach first? The right side of the train or the left side of the train? Okay, if you thought the answer was same, unfortunately, you're wrong, because just imagine this. The train is moving at a very fast fraction of the speed of light. That means the back end of the train will actually receive the light first because it's moving towards it, and the front end of the train will receive it last because it's moving away from the light. Simple enough. And he figured out several experiments to do this and to test this. And this time dilation and the light effect were all proven by Einstein. So that's the basis of special relativity. I may go on to the other facts about it in another video, but that's it for now. Thank you.